How a motion can be understood, or what restrictions are on the motion from these concepts. So, we started in those lectures from number 1, the principle of conservation of linear momentum, and what it said was that if I have many particles interacting with each other, as long as these interparticle forces obey Newton's third law, the net momentum, that is m I v I product summed over, is a constant if summation of external forces on each of the particles is 0. That is, if the net external force is 0, the momentum, the total momentum of the system remains a constant. In other words, I can write d over dt of summation m I v I is equal to 0, and that is the principle of conservation of linear momentum. Related with this, when we considered momentum of many particles, was the concept of center of mass, which was defined. Suppose there are many particles at different positions. Let me call this one r I, let the mass be m I, then the center of mass coordinate r equal to summation m I r I over summation m I. The beauty of center of mass was, or is, that if I apply an external force, no matter how these particles are moving, they may be doing anything, the body may be deforming, the orientation may be changing, but the center of mass always moves as if the entire mass is sitting there and the net force F external is applied there, where m is the total mass of the system and F external is the net force, that is summation of F external I on each individual. In other words, if F external, the net external force is 0, I am going to have RCM dot is equal to constant. That is, the center of mass would keep on moving with constant velocity. We solved one example using this in the previous lectures. Third thing that we learned was the conservation of total mechanical energy, and what it said was, in a conservative field where the work done is independent of the path, the kinetic energy plus the potential energy of a system of particles is constant. In this lecture, we are going to look at these principles once again through examples to learn how we can use them effectively to learn about motion of these particles. As the first example, I am going to take two particles colliding with each other and going out. Let the particles be m1 and m2 masses. This is coming in with velocity v1, this is coming in with velocity v2, this is going out with velocity v1 prime, again m1, and m2 goes out with velocity v2 prime. I am going to assume that the interparticle forces act only in a very small region, so that before the collision and after the collision the particles are essentially free. The other thing I am going to assume is that this region is very small, and therefore, during the interaction when the particles go in, interact and come out, they hardly move. So, P e, the potential energy, remains roughly the same, and therefore, I can write by energy conservation that the K e, or the kinetic energy coming in, which is 1/2 m1 v1 square plus 1/2 m2 v2 square, plus I will add a term delta E to take care of energy which may be released during their interaction or which may be lost during interaction. So, this must be equal to 1/2 m1 v1 prime square plus 1/2 m2 v2 prime square. That is what energy conservation gives me. If, or let me write the equation again and then we will talk about delta E. So, the energy conservation gives me 1/2 m1 v1 square plus 1/2 m2 v2 square plus delta E is equal to 1/2 m1 v1 prime square plus 1/2 m2 v2 prime square. Now, if delta E is greater than 0, that means the kinetic energy after interaction is going to be more than the kinetic energy that was coming in, and that means some energy has been released during the interaction. So, this implies energy released during collision. This may be the case, for example, two particles colliding and some internal energy comes out. If delta E is less than 0, energy is lost during interaction, and this is usually the case which we call inelastic collisions. And third case may be that delta E is 0, and that is an elastic collision. So, we have seen what the conservation of energy is going to give us. I remind you again that we have assumed the region of interaction is so small that the potential energy hardly changes, and the energy between the particles is essentially that of free particles, and therefore, I am writing only the kinetic energy. The other principle is going to be the principle of conservation of linear momentum, and that tells me that summation m I v I is a constant if there is no external force. Since the interaction time is very small, we neglect any external force impulse that may be acting on the particles. So, we assume that impulse due to F external is essentially 0, and therefore, the only force that acts during that interaction time is that of the particles applying each other on each other, and therefore, I am going to have m1 v1 plus m2 v2 is equal to m1 v1 prime plus m2 v2 prime. If there is external force, I can always take care of that by adding terms here, but for simplicity we are ignoring it right now and assuming that the interparticle force is really much larger than this. So, we are taking the simplest possible scenario of two particle collisions and getting two conservation principles that tell us that the energy is conserved. Therefore, this equation must hold 1/2 m1 v1 prime square plus 1/2 m2 v2 prime square, and the other equation that should hold is m1 v1 plus m2 v2 is equal to m1 v1 prime plus m2 v2 prime. In case you have lost track of what's going on so far, let me remind you, two particles are coming in, interacting in a very short, for a short time in a very small region and going out. This particle has mass m1, this particle has mass m2, coming in with velocity v2, coming in with velocity v1, m1 goes out with v1 prime and m2 goes out with v2 prime. This is one equation, and for each component I can write one equation in this. So, this is in effect equation number 2, equation number 3 and equation number 4. Therefore, I have 4 equations from which to extract information about the motion. The number of unknowns that I want to know after the interaction has taken place is v1 prime 3 components and v2 prime 3 components. Therefore, total number of unknowns that are involved in this are 6, whereas the number of equations that arise out of conservation principles are only 4. Therefore, using conservation principles, I cannot get the motion fully, or I cannot get all the 6 unknowns fully. For that, I really have to solve the equation of motion. However, now I am going to show you that these principles put constraints on motion and therefore are useful to tell us about what can happen, what may not happen. So, let us look at an interesting case where two particles come in with velocity v1, m2 with velocity v2 get stuck together, so that out goes a particle of mass m1 plus m2 with some velocity v. Then the energy conservation principle tells me that 1/2 m1 v1 square plus 1/2 m2 v2 square plus delta E, which is the energy released or lost during this interaction, must be equal to 1/2 m1 plus m2 v square. And the momentum conservation tells me that m1 v1 plus m2 v2 must be equal to m1 plus m2 v. Let us see, by using these two conservation principles, what can I learn about the motion or the restrictions on the motion. From this equation I am going to substitute here. Before that, let me cancel this 1/2, 1/2, 1/2, put a 2 here, and now substituting this v here, I get m1 v1 square plus m2 v2 square plus 2 delta E is equal to m1 plus m2, and I substitute for v, which is m1 v1 plus m2 v2 with vectors here, square divided by m1 plus m2 square, which is equal to, I can take away this power, and therefore I get m1 plus m2 m1 v1 square plus m2 v2 square plus 2 delta E is equal to m1 v1 square plus m2 square v2 square plus 2 m1 m2 v1 dot v2. In case you have gotten lost, let me remind you what I did. I wrote the energy conservation principle, I wrote the linear momentum conservation principle, and from the linear momentum conservation principle, I substituted for the final velocity in the energy conservation principle, and I am just rearranging the terms. Collecting them, I am going to get m1 square v1 square plus m1 m2 v2 square plus 2 delta E m1 plus m2 plus m1 m2 v1 square plus m2 square v2 square is equal to m1 square v1 square plus m2 square v2 square plus 2 m1 m2 v1 dot v2. This fellow cancels with this fellow cancels with this, and I get, rearranging terms, I will take it to the left hand side. I will get m1 m2 v1 square plus v2 square minus 2 v1 dot v2 is equal to minus 2 delta E m1 plus m2, or I can write this as v1 minus v2 square, and therefore get v1 minus v2 square is equal to minus 2 delta E m1 plus m2 over m1 m2. This is a very important result, and now we are going to see what all it teaches us about the motion. Let me write this again on the next slide. What I have obtained by combining the two conservation principles, v2 minus v1 or v1 minus v2 square is equal to minus 2 delta E m1 plus m2 over m1 m2. Notice that the left hand side is a perfect square, so it is always greater than 0. On the other hand, right hand side, so this is the left hand side, the right hand side could be greater than 0, 0 or less than 0 depending on the sign of delta E. If delta E is greater than 0, then the right hand side is less than 0, and therefore, the left hand side and the right hand side can never be equal if this condition is satisfied. What does this mean? Recall again, what are we doing? Two particles coming in, interacting and going out as one particle, m2, m1, m1 plus m2. If during the interaction some energy is released, that means delta E is greater than 0, I can never satisfy this equation, and this interaction will never take place. So, if two particles during interaction release energy, they will never get stuck together and go out as one particle. For example, if two atoms collide and make a molecule, they will never do it in free space if during their formation of that molecule some energy is released. On the other hand, if delta E is less than 0, then right hand side is greater than 0. That means during the interaction some energy is released, some energy is lost, and that is an inelastic collision, and this does take place as you have seen in your 11th and 12th grade also. Third case, if delta E is equal to 0, that interaction is also not possible because the right hand side is 0 and the left hand side is greater than 0. So, this is an elastic collision. In an elastic collision, two particles will never really get stuck together. Through the example that we just solved, we saw how the combination of two conservation principles tells me whether a particular reaction or a particular collision is allowed or whether it can take place or not. The other concept that we have introduced in the past two lectures is that of center of mass and In the coming few minutes, I want to spend some time on this to show how important a concept it is and how it makes solving problems easy at times. As I told you earlier, if there is no external force, then the center of mass moves with a constant velocity. If it is moving with a constant velocity, then if I attach a frame of reference to the center of mass, so let us attach a frame of reference to the center of mass, or in short Cm, that frame is also going to move with a constant velocity, and therefore that is going to be an inertial frame. If it is an inertial frame, Newton's second law is valid there also, and I can equally well describe the motion of particles in this inertial frame attached to the center of mass, which I am going to now on call the Cm, or the center of mass frame. Why would I want to do that? So, why should I describe motion, and in this case, since I am taking example of two particle system, so let me write motion of two particles in the Cm frame. Why should I do that? Recall that by definition Cm frame is such that the total momentum of particles in this frame is 0. Again, going back to two particles, m1 moving with v1, m2 moving with v2 in the frame attached to the ground, which I am going to call the lab frame. Lab because usually collision experiments are done in a laboratory, and therefore I am going to call this a lab frame. I have m1 v1 plus m2 v2 is equal to m1 plus m2 vcm. By definition, on the other hand, if I go to center of mass frame, the velocity in center of mass frame, which I am going to refer to as v1c, is going to be v1 minus vcm, and v2c is going to be v2 minus vcm. Combining this equation, and this equation, you can see right away that in the center of mass I am going to have m1 v1 minus vcm plus m2 v2 minus vcm is equal to 0, or m1 v1c plus m2 v2c is equal to 0. The net momentum in the center of mass frame is always 0. That is understandable. By definition, if I am sitting on the center of mass frame, the velocities are such that the net momentum has to be 0, and therefore if the particles are colliding, if one particle in the center of mass frame is moving like this, the other one is going to move like this. After collision also, since the net momentum is 0, no matter what they do, whether energy is lost, energy is gained, whatever, they will again either go in opposite direction or move towards each other. So, if this was m1 in Cm frame, it was coming in with velocity v1c, m2 coming in with velocity v2c, so that the net momentum is 0. Out goes this with m1 v1c prime, m2 with v2c prime, again the net momentum is 0. Let us see it clearly, what happens in the lab frame and what happens in the center of mass frame. So, let me draw a line here. In the lab frame, that is sitting on the ground or sitting in my laboratory where I am doing the experiment, one particle comes in, the other particle comes in, this is m1 v1 m2 v2, m1 goes out, m2 goes out with different velocities v1 prime and v2 prime. In the center of mass frame, m1 comes with v1c, m2 has to come with opposite velocity m2 v2c, so that the net momentum is 0, and m1 goes out with v1c prime, m2 has to go the other way, m2 v2c prime. The center of mass, of course, if it was moving like this, will keep on moving as it is. So, let us say this was the center of mass, this during entire interaction it will keep on moving like this. So, no matter what is happening, delta E, as we introduced earlier, may be greater than 0, delta E may be less than 0, or delta E may be equal to 0. This picture will always remain. The particles will always move in opposite directions, and that simplifies the description of motion. Of course, finally, to compare with the result of experiments, I have to transform back from center of mass to my lab frame. So, this is good for calculations, and this is the comparison. The lab frame is a comparison with experiments. So, I should also be going back and forth between the two systems. I should know how to do that. To start with, I will take a simple example of elastic collision, again between two particles, and describe it in the center of mass, and also see how to go from center of mass to the lab frame. Recall that in an elastic collision, delta E is equal to 0, and therefore, in the center of mass frame, I am going to have half m1 v1 c square plus 1 half m2 v2 c square is equal to 1 half m1 v1 c prime square plus 1 half m2 v2 c prime square. Similarly, I am going to have m1 v1 c plus m2 v2 c is equal to 0. And recall, in center of mass frame, since this is 0, the velocities have to be opposite to each other. So, I can write this equation in a simpler form as m1 v1 c minus m2 v2 c is equal to 0, and after the collision the particles go out again in directions opposite to each other. I am going to have m1 v1 c prime minus m2 v2 c prime is equal to 0. You may feel there are more variables in this than the equations, or there are more equations here than the number of variables, but that is not true, because in this frame I am not telling you what this angle of scattering is. For example, the particle 1 comes in like this, it is getting scattered by this angle, which I will call theta cm. We are not specifying that. I can't really solve for that unless I know the equation of motion. But let us see what these three equations tell me. So, I have 1 half m1 v1 square c square plus 1 half m2 v2 c square is equal to 1 half m1 v1 c prime square plus 1 half m2 v2 c prime square, and the other equation is m1 v1 c prime minus m2 v2 c prime is equal to 0. As I told you, I have v1 c prime, v2 c prime. The only thing I can get from these two equations then is v1 c prime and v2 c prime. I cannot specify this scattering angle. Okay, this is consistent with what we learned earlier, that conservation laws can give you only some information about the motion, but not all. if I want to get this theta Cm, I really have to solve the equation of motion, and I must know in detail what the interaction is. But going back to the equations of conservation, applying these two together, I get V1c prime is equal to m2 upon m1 V2c prime, and let me substitute this in the energy conservation equation to get 1/2 m1 V1c square plus 1/2 m2 V2c square is equal to 1/2 m1 V1c prime. I will substitute this, I get m2 square over m1 square V2c prime square plus 1/2 m2 V2c prime square. How about the left hand side? I can use the same trick on the left hand side to get V1c in terms of V2c. Recall that like this I also had, like this equation, the momentum conservation equation, I also had m1 V1c, I am writing on the left bottom corner, minus m2 V2c is equal to 0. So, I can make this substitution here to finally get 1/2 m1 m2 over m1 square V2c square plus 1/2 m2 V2c square is equal to 1/2 m1 m2 over m1 V2c prime square plus 1/2 m2 V2c prime square. Now, you see the common factor, this and this together are the same, and this implies V2c is equal to V2c prime square, or the magnitude of V2c remains the same during the collision. If this is the case, then obviously V1c also remains the same as V. The particles collide and go out. Graphically, what is happening is this particle is coming in, let us say with V1c. All that happens during the collision is this vector, its length remains the same, just rotates by angle theta Cm. As I said earlier, I can't really calculate theta Cm using conservation principles. Similarly, V2c, this is V1c prime. V2c comes in, and all that happens during the collision is this also rotates by an angle theta Cm. So, this is V2c, V2c prime, as simple as that. Of course, if I want to compare the results that I get with the lab results, I have to transform back to the lab. That we will see in a minute. But this is so simple. So, if I make a circle, this was V1c, and this is what happened to it after the collision. Suppose this was the center of mass velocity. Then from here to here was V1 in the lab frame, and after the collision Vcm plus V1c prime is going to be the velocity in the lab frame, and therefore, this is going to be V1 prime. This was theta Cm, and this is theta lab. So, looking at the motion in center of mass frame, I find that if this was Vcm and in the center of mass frame this was V1c, all that happens during the collision with particle 2 is that this particle moves in this direction, its direction of motion rotates by theta Cm, so that its final velocity is V1 prime in this direction, and obviously this particle was moving like this. So, it has scattered by this much theta lab. The relationship between the two is very clear now. I have tangent of theta lab is equal to, if I drop a perpendicular here, it will be V1c magnitude sine of theta Cm divided by Vcm plus V1c cosine of theta Cm. Notice in this case I have been making Vcm and V1c in the same direction. That is the assumption. This need not be the case always. This, however, is the case if I take mass 2 to be stationary and mass 1 to be coming in with some velocity V1. So, this formula is correct in this case when Vcm and V1c are in the same direction. On the other hand, if I have one mass coming in like this in the lab frame, the other mass going in like this in the lab frame, this is M2, this is M1, then Vcm would be moving, would be something like this. So, center of mass would be moving in this direction. They will not be co-directional, and the relationship between theta lab and theta Cm would be slightly more complicated. So, the simplest case that we have considered is when Vcm and V1c are in the same direction, and therefore, this I said is the case where mass M2 is stationary and mass M1 is moving in. Let us see what we learn from this relationship. So, we specialize to a case where mass M2 is sitting, mass M1 is coming with, say, velocity V1. Then Vcm by definition would be M1 V1 over M1 plus M2. V1c would be equal to V1 minus Vcm, and therefore, M2 V1 over M1 plus M2, and V2c would be equal to, since mass 2 is stationary to start with, minus M1 V1 over M1 plus M2. You can see that M1 V1c plus M2 V2c is equal to 0. So, this is Vcm, V1c, and this just rotates in elastic collision by theta Cm. Therefore, this is theta lab. I have tangent of theta lab equal to V1c sine theta Cm divided by Vcm plus V1c cosine of theta Cm, or tangent of theta lab is equal to sine of theta Cm divided by Vcm over V1c plus cosine of theta Cm. Let us see the picture again. This was Vcm, V1c, V1c prime, theta Cm, and this is theta lab. Now, we said when V2 or the mass 2 was stationary, Vcm was equal to M1 V1 over M1 plus M2, and V1c is equal to M2 V1 over M1 plus M2, and therefore, Vcm over V1c is equal to M1 over M2, and this implies that tangent of theta lab is equal to sine of theta Cm over M1 over M2 plus cosine of theta Cm. So, we applied the conservation principles in center of mass frame. In this, in an elastic collision, the magnitudes of the velocities in the center of mass frame remain the same, they just change direction. The total energy is conserved. Now, let us see the case when m1 over m2 is greater than 1. That means, the particle which is coming in is heavier than the particle on which it is hitting. In that case, you will see that tangent of theta lab is equal to sine theta Cm over some number which is greater than 1 plus cosine of theta Cm. The minimum value of cosine theta Cm is minus 1, and therefore, theta lab is going to actually show a maximum. Tangent theta lab is equal to sine theta Cm over m1 over m2 plus cosine of theta Cm. If I plot theta lab versus theta Cm, it will show some sort of a maximum. Let us try to understand that graphically, but before that, you try to recall from your everyday experience. If you hit a very, very heavy ball on, say, a marble, a kancha, you see it does not really deflect back, it always goes forward. There is a maximum angle through which it can get scattered. On the other hand, do the other way, hit a kancha on a very heavy, say, cricket ball, it can go in any direction. So, when m1 is greater than m2, that is, I am hitting a cricket ball, throwing a cricket ball on a stationary kancha, it always deflects forward. There is a maximum angle. To understand this graphically, let us make V Cm. Recall V Cm is equal to m1 V1 over m1 plus m2, and it is greater than V1c, which is equal to m2 V1 over m1 plus m2. So, this vector is smaller in magnitude than this, and V1c can go in any angle. This is theta Cm and this is theta lab. You will see that as this vector V1c prime vector rotates, theta lab is going to become a maximum when this touches it like this, when this is theta Cm, and then again going to become smaller. So, we see graphically also how the angle theta lab is actually has a maximum. It has a maximum when V1 prime is this tangent, and you can see from here that for sine theta max in lab is going to be this divided by this, or V1c over VCm, which is m2 over m1. Let me show it more clearly again in the next slide. When m1 over m2 is greater than 1, this implies VCm is greater than V1c in magnitude, and therefore, this is VCm. I draw a circle from here of radius V1c, and that shows how much V1c can rotate. The lab angle would keep on increasing if the V1c is here, 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 and at this point where this becomes a tangent, theta lab would be a maximum, and as V1c rotates further, theta lab would become smaller, as you can see. So, sine of theta lab maximum is equal to V1c over VCm, which is equal to m2 over m1. Recall again, this is the case when m2 is initially stationary and m1 is coming in with velocity v1, and m1 is greater than m2. In that case, there is a limit of scattering angle in the lab. On the other hand, so this is the information that we have obtained by looking at the motion in center of mass frame and then transforming to the lab frame. On the other hand, if m2 is greater than m1 and still stationary and m2 stationary in the beginning, then VCM is going to be less than V1C, because VCM is m1 V1 over m1 plus m2, V1C is m2 V1 over m1 plus m2, and m2 we are taking to be greater than m1. In that case, VCM would be this, but V1C would be larger in magnitude, and this, when it rotates around, the lab velocity can make any angle. So, we learn that in these collision processes where m2 is stationary, m1 comes and hits it. If m1 is greater than m2, it is like a cricket ball hitting a marble. There is a maximum angle through which the cricket ball would get deflected. On the other hand, if it is a marble hitting a stationary cricket ball, marble would go at any angle, as you can see from this picture. So, we see that in an elastic collision, when two particles collide, again I am taking a general case where one particle is not necessarily stationary, m1 comes in with velocity v1c in the center of mass frame, m2 comes in with velocity v2c in the center of mass frame, and they go out, v2c prime, v1c prime, m1, m2. If the collision is elastic, then v1c was equal to v1c prime and v2c is equal to v2c prime. This is a general result which we in the previous case applied to the case when one particle was stationary to start with and other particle hit it. Now, let us see what is the consequence of this. In the lab frame, the relative velocity of particle 2 with respect to particle 1 is this. Let us see what happens in an elastic collision to the square of this. I can write this as V2 is, recall, VCM plus V2C minus V1 is VCM plus V1C. So, this I can write as VCM minus V1C, which is equal to V2C minus V1C square. All it says is that the difference of velocities V2 minus V1, in whichever frame you see it, the relative velocity is the same, V2C minus V1C, and I am making use of that in just looking at the square, V2 minus V1 square is equal to V2C minus V1C square, which I can write as V2C square plus V1C square minus 2 V1C dot V2C. Recall that in center of mass frame the particles are moving opposite to each other. So, the angle between them, their velocities, is 180 degrees, and therefore, I can write this as V2C square plus V1C square plus 2 V1C V2C. Also recall that when the collision is elastic, the velocities, magnitudes or their squares remain unchanged, and therefore, I can write this expression further as V2C prime square plus V1C prime square plus 2 V1C prime V2C prime. And I can therefore skip some steps and write that V2 minus V1 square is equal to V2C minus V1C square, which is then equal to V2C prime square plus V1C prime square plus 2 V1C prime V2C prime, which would be equal to V2C prime minus V1C prime square. Change this into a dot product again using the fact that V1C prime and V2C prime are also at 180 degrees. So, what do you see? That in an elastic collision, the relative speed square, the speed of approach and speed of separation remains the same, which you have learned in your elementary courses, that in an elastic collision, the speed of separation is the same as speed of approach, and that is precisely what I have derived here. Again, using the center of mass frame, or the coefficient of restitution is equal to 1. So, this is another example of how we can quickly derive these results going to center of mass frame and how we can use these principles. If you want to see a really dramatic effect of two particle collision, I will give you a one dimensional example. Take a TT ball and put it on top of what they call in the market crazy ball. This ball really jumps very high, its coefficient of restitution is almost 1. Balance it and drop it on the ground from, say, a height h, and observe what happens after it hits the ground. You will see that the TT ball really takes off. So, calculate what is the maximum height up to which the TT ball will rise after the crazy ball hits the floor. Perform this experiment and try to justify it using whatever you have learned so far. Assume all the collisions to be elastic, and that will give you the maximum possible height. Also, while solving the problem, assume that TT ball and crazy ball hit when they are going against each other, because by the time the lower crazy ball hits the floor and goes up, the TT ball is still moving down. I will give you the answer. The answer comes out to be 9 times the height from which you drop it. So, if you drop it from 1 meter, it will really hit the ceiling. Do this experiment, see, and try to see if you can get this result theoretically from whatever you have learned so far. You should be able to do so. Having done the examples of elastic collisions, let us now ask what happens when inelastic collisions between two particles are going to take place. For that, what will happen is two particles which are coming in the center of mass frame with V1C, V2C. Since the momentum still must remain 0 when they go out after collision, V1C prime and V2C prime would still be in opposite directions, but their magnitudes may become smaller. How much energy loss takes place? How much is the maximum energy that can be lost? Those are questions that are raised in an inelastic collision. So, let us try to answer that. For that, I am going to use a result for the kinetic energy of these particles, and I am going to show that kinetic energy of a system of particles is equal to kinetic energy of the center of mass plus kinetic energy about the center of mass. We are going to use this result here to see how much is the maximum energy loss that can take place during an inelastic collision, but this result by itself is of great importance and we will use it quite a lot later when we describe rotational motion of extended bodies. So, to see this, let us write kinetic energy of a system of particles is nothing but 1/2 m I V I square summed over I. Let me now use the fact that V I is nothing but V of the center of mass plus V I C, that is the velocity in the center of mass frame, and therefore, the kinetic energy can be written as 1/2 summation I m I V C m plus V I C whole square, and this comes out to be 1/2 summation I m I V C m square plus V I C square plus 2 V C m dot V I C. Let us write these three terms separately to get kinetic energy is equal to 1/2 summation m I V C m square plus summation 1/2 summation m I V I C square plus 1/2 V C m dot V I C, and there is an m I here and summed over I. This term I can write as 1/2 V C m is a constant that has no index I. So, summation m I is total mass V C m square. This term I can write as K E about C m, because V I C measures the velocity about the center of mass, and for this term V C m I can again take out and write this as V C m over 2 summation m I V I C dotted here. However, this is the momentum in the center of mass frame and therefore 0, and therefore, the only two terms which are left are this, and I can write the kinetic energy of the system as 1/2 m V C m square plus 1/2 m I V I C square. The third term gave you 0, which is nothing but K E of center of mass plus K E about the center of mass. This is the beauty of center of mass. Later when we do rotational dynamics, you will see that I can do a similar composition for the angular momentum also. To see an example of this, let us take a rotating rod. Suppose I throw this, so that the center of mass is moving in one direction if it is force free motion, but the rod is rotating. The next time its orientation could be this. Then I could write its kinetic energy as the kinetic energy of its center of mass plus the rotational energy about rotational kinetic energy about the center of mass. We will be making use of this again in discussing rotational dynamics. But what interests us here is that now if two particles or more are interacting, colliding and then going out, I should have the net momentum P always conserved. So, that is going to be summation m I V I, which is a constant. The K E of center of mass I can write as P C m square over 2 total mass. Since P C m is a constant, mass is a constant, this term would always remain there no matter what, whether energy is lost or whatever. The kinetic energy of the center of mass is going to be P C m square over 2 m, whereas the total kinetic energy is K E C m plus K E about C m. this must always remain there because of the momentum conservation. So, the maximum energy that I can lose in an interaction is Ke about C. This is another result of importance and shows us how going to center of mass sometimes helps. In fact, a lot of times it helps, and we will be making use of it again and again. To conclude, in this lecture, I have taken some examples to show you the importance of application of conservation principles, how they can give us some information about the motion when particles interact, although the full information has to be obtained only through the solving of the equation of motion. Lot of important restrictions can be derived based on conservation principles.